Good morning to one and all. My name is J. Chinnaranga. Currently, I am pursuing my graduation in BTech first year in the ECU department. So, in the part of the CA2 video representation, the topic which was assigned to me is direct and indirect band gap of the semiconductors. Direct and indirect band gap of the semiconductors. First, we would have to understand the key differences and the implications of the direct and indirect band gap of semiconductors. First of all, we should know about the semiconductors, what is meant by band gap, and what are the uses of the band gap. And we should know about the characteristics and the applications and the implications according to the electronic and optoelectronic industries. Because if we are going to study about anything, first we have to look forward for what purpose it should be used, and in what purpose it is going to be benefit us. Okay, this presentation explores the fundamental differences between the direct and indirect band gap of semiconductors. We will be going to discuss the characteristics, applications, and the implications for the electronic and optoelectronic industries. Understanding these concepts is crucial for the advancements in the technology and material science. As I said before, this direct and indirect band gap of semiconductors is must be study is very crucial in order to advancements in the technology or the developing the technology and the material science. Okay, first of all we would see first we will see the introduction. What is importance of the semiconductors in electronics? Why the semiconductors are used? First of all, what is meant by a semiconductor? Semiconductors are the devices which conduct the electricity partially. For example, helium, germanium, silicon are the examples for the semiconductors, because at absolute temperature they act as the insulators, and above the absolute temperatures they will be acting as the conductors. So as acting as a conductors, they will be not allowing the current to pass through them, but they allow the current partially to flow off them. Okay, next, semiconductors are crucial in modern electronics, enabling devices like computers, smartphones, and solar panels. Their unique properties allow the control of electrical conductivity, making them essential for various applications. The band gap is the key factor in determining the semiconductor's conductivity, optical characteristics, and influencing its usability in technology. As I said before, semiconductors are very very crucial in modern electronics, such as we have been doing the experiments like PN junction diode and so on, which are also called as a semiconductors, which play a very vital role in the electronics and the electrical circuits. Next, on behalf of all we are studying that on behalf of we are studying that semi direct and indirect band gap of semiconductors. So first of all, what is meant by a band gap? The band gap is defined as the energy difference between the valence band and the conduction band, and these electrons need energy to move from the conduction band for conduction, and the types of band gaps are the direct and indirect. Next, what is meant by direct band gap of semiconductors? First, next, direct band gap semiconductors have their valence and conduction bands aligned at the same momentum, in which the electrons which are at the valence band and the conduction band have been aligned at the same momentum, and this allows the direct transitions for the electrons, enabling efficient light emission such as LEDs and laser diodes. Common examples include gallium arsenide, GaAs, and indium phosphide, which are vital in optoelectronic applications. And these direct band gap semiconductors have the same momentum, have aligned in the same momentum, which is very the electrons in the conduction band and the sorry in the electrons in the conduction band and the valence band are having the same momentum, and whereas in the indirect band gap there will be different momentum. And here is the visual diagram of the electric transition of indirect band gap of semiconductors. Here we can see that the electrons are aligned in the same proportion, but they will be having a different momentum, as we see that the red lines and the green lines in the diagram. And there will be occurring a transition for platinum photon energy, which results in the difference in the momentum in the conduction band, or either in the valence band. Okay, now from now I am saying till now I am saying direct band gap and indirect band gap. So now let's talk about the applications of a direct and indirect band gap. Okay, understanding their practical uses: optoelectronics, LEDs, and laser diodes. As we talked in the as we have discussed in the direct band gap, the this same momentum will be used. This same momentum will be used in the preparation of LEDs and laser diodes. These characteristic will be used to prepare the LEDs and the laser diodes, which are a very vital role, which play a very vital role in our daily life. And there will be a high efficiency of solar cells. If from nowadays we are seeing that many of the colleges or the many of the houses are implanted by not are implanted by direct current. There will be implanted by solar panels which save the current, which save the electricity, which will be running behalf of the sunlight. And those solar cells are having the high efficiency due to the direct band gap. And the electronics devices like transistors, microchips are also having the direct band gap. Applications of the direct band gap and the indirect band gap is here. Then next, what are the pros and cons of each band gap? Pros means the advantages of each band gap. Disadvantages means the cons of each band gap. So therefore, first of all, we will observe direct band gap. In the direct band gap, efficiency of light emission is higher, because if we see in the, as we said, the LEDs and the lasers are made up in the energy band gap of a direct band gap of a semiconductor. Due to that same momentum, there will be an higher efficiency in light emission. Whereas if we come to the indirect band gap, it is easier to fabricate, and there will be a difference in the momentum in the conduction band and the conduction band and the valence band. Therefore, there will be easier to fabricate. And in the direct band gap, there will be faster electronic transitions. There will be faster electronic transitions, such as we discussed in the PN junction diode and so on in the electronics. And cost effective, and where we come to the indirect band gap, cost effective for electronics. These are also fast in electronic transitions, but these include some amount which are very costly. And if we come to the direct band gap, there will be, it is very better for optoelectronics, which means there will be a higher performance, there will be a higher technology for which will be using in optoelectronics. And in the indirect band gap, there will be a stable performance in the devices. If we use the same if we use the same type of device for the direct band gap and the indirect band gap, there will be a better there will be a better output, or there will be a better technology in the direct band gap. Whereas in the indirect band gap, there will be only stable performance in the devices. And at lastly, the conclusion is, in summary, direct band gap semiconductors efficiently emit light, making them ideal for optoelectronic applications, while indirect band gap semiconductors are more suited for electronic devices due to their stability and cost effectiveness. Selecting the appropriate band gap is crucial for optimizing material performance in various applications. Future trends indicate advancements in material engineering, such as the use of quantum dots and 2D materials. As we discussed before, the direct band gaps and the indirect band gaps may change the future technological apparatus, such as the mobiles or the laptops or the computers, which will be used by the further generations. And this is the main very important topic in designing the circuits in designing the circuits of any electronic appliance. And this may be helping to overcome the limitations of indirect band gap semiconductors. And thank you for giving this opportunity.